So the elements that you get in the title, so one of the points that is maybe something you should know if you haven't ever met this, it's called the Duality Gap, and it's very useful for stopping algorithms. This is a good criterion. We're going to develop that some more, but it's a very interesting concept that I didn't know 2 years ago, so I mean, I'm glad I can share my new knowledge with you. It's very interesting. And based on those elements, I'll show that we can create some interesting rules that people have called safe rules or safe screening rules. And they allows you to discard elements earlier in your algorithm so that there's a lot of computation that you will avoid doing. And this is more or less what we have been doing. So I will focus mainly on the Lasso. The extension initially I was planning to do it for the multitask regression, but I think that the mathematics involved are just a little bit too messy for nothing. You'll see, I will present the formalism. If you're interested in the multitask, I'll give you the paper, and you'll see it's nothing more fancy, it's just more computation. So let's try to make it as simple as it is already for the Lasso and its variant. So it's this time it's an ongoing work with a bunch of people from my university. It's with Olivier Fercoq, who is a new assistant professor. He used to be a postdoc last year. With Alexandre Gramfort, who is also a colleague of mine, mainly interested in imaging, brain imaging. So he has really in mind improving those detection, those reconstruction algorithm for fMRI and EEG. And Eugene Ndiaye, who is a recent hired grad student, so he's starting his PhD like those days. So he's a newcomer in the department. So okay, I'll be back and on what we have seen yesterday for the motivation, just so that we have been sleeping too little this week or this night. We'll come back to what we have seen yesterday. So again, I will motivate the fact that in modern statistics, image processing, machine learning, there are atoms that you are interested in using and you want to use only a few of them. So we have seen Fourier, wavelets, dictionary learning. There are many of them. And as yesterday I presented to you, we want to use a model that is leveraging on sparsity. So I try to make use of the same notation. So again, Y is going to be the signal all along, either an image, a sound, or something else. It could be from statistics, just an experiment where you have seen a bunch of people and analyze data on themselves. X is still going to be the dictionary or the design matrix, as I will use the two names for those elements. And again, I will try to model my signal Y as a sparse combination of the elements, the atoms of my dictionary. So this is the model we have seen yesterday quite a bit, extensively. So it's just going to be the same. X1, XP are the P atoms in the dictionary. Beta 1, beta P are going to be the coefficient. And we want only a few of them to be active. And again, P, N can be large, both of them, and you want beta sparse. So let's go back to the Lasso, just so that we remember what it is. The Lasso is just a minimizer, so it's non-unique. I mentioned that yesterday, of a data fitting term plus a regularization with the L1 norm. So we have seen and studied quite a bit extensively this algorithm. We have seen that depending on the choice of lambda, the solution is going to be sparse, and we can control the sparsity with the choice of lambda. Of course, we need to tune or choose lambda, and I mentioned to you yesterday that cross-validation might be like an option. There are others, but usually what you have to do is compute a lot of lassos for different values of lambda, and then try to pick the best one. And we're going to see that algorithmically, we will have to do it in a clever way so that we don't have to pay the price for optimizing many problems, because most of the problems will be similar. So we'll leverage on that. So I was a bit short on time yesterday. I didn't give you all the theoretical guarantees. If you are interested, again, you can just look, for instance, at this paper by Bickel, Ritoff, and Sebakov. This is maybe like the most extensive review of the properties of the Lasso. And again, there are many refinements. I'm not claiming the Lasso is the ultimate goal and the ultimate tool, but it's a brick that you should maybe use or adapt depending on your problems. So you can do adaptive lasso. We have seen yesterday least square lasso. There's square root lasso when you don't know the name, the noise level. Those two elements, in fact, are the same. It's just 2 point of view that was leading to the same estimator or constriction. The people didn't realize it, but it's just the same. So, okay, so let's go back to the different points we had in mind to compute the lasso solution. As an algorithm, we need something that produces an approximate solution of the optimization problem. So we have seen 2 of those different guys here in details. So I will just comment briefly the first one. I mentioned to you that the lasso, in good cases, so in the common cases, in fact, has an affine, it's a piecewise affine restriction. So it means that, okay, I know the solution at the beginning of the path. You remember when lambda is big, it's 0. And then when lambda gets smaller and smaller, I have some kind of lines that I can compute. And in fact, since we know this structure specifically for the lasso, some people have adapted methods to say, okay, all I need to know, since it's affine, I just need to know the slope. And I can leverage that. So you need to compute the slope, and then the moment where a new variable will either pop in or pop out of the model. And so people have been using that. The only bad news for that is that it's totally restricted to the lasso. If you do, for instance, group lasso, if you do classification using logistic regression, all this gonna fail. So it's a convenient algorithm, but only for one particular class. So it's not something that you can generalize. However, we have seen like those 2 classes of methods, the forward, backward, and the coordinate descent. And both of them can be used with some limitation, but they can be used for generalization of the lasso, and they're pretty convenient. So we have seen that forward, backward would be more interested for cases or proximal algorithms that are kind of similar. They are more interested when you can compute efficiently the inner product between the residual, more or less, of your problem, with the interaction with the atoms of your element. If you analyze this matrix, in fact, it is just computing the inner product between the atoms of the dictionary and the residual. And if you can perform this efficiently, then go for it. And here in the presentation today, I will mostly focus on the coordinate descent at the end. So this is something, this is, let's say, my choice. And this is also because we were trying to update some software that are based on this element. But what I will present might help to accelerate both of those kind of algorithms. And for this one, that won't work. But as I told you, I'm not really interested in the homotopy methods. So just a few remarks, maybe that to refresh what we have seen earlier. So this is, again, the same problem. We mentioned that we have to compute many lassos. It's just lambda is unknown, so the best you have to do is compute different values of lambdas. And yesterday I told you, okay, well, there is at least one good news, is you know where to start. And where you should start is at this very value, which is the critical lambda max, where at this stage, 0 is the solution. And if it's greater than that, if lambda is greater than that, you don't have to compute it, it's just 0. However, now you need to like find a grid or construct a grid on which you're gonna evaluate the lasso. So is this grid usually linear? The answer is no. People use more log scale grid, meaning that you can go through different, let's say different scale. And the usual is to say, okay, I take lambda max that I know, and I take a small coefficient epsilon, like epsilon is 0.1 or 0.000, whatever you prefer, and you pick a number. For instance, the default in many software is like 100 values of lambda, and you say, I'm gonna compute like those 100 values of the elements. So this is what we're gonna do in the. So I already mentioned this. We're gonna adapt our speed up strategies to different algorithms. And also, one of the points that I'm interested in is like, even though you see there is a bit of math involved to design our new rules, you will see that they are very easy to code, in fact, and just like, if you got a solver, I'll give you an ingredient that you can add to your solver, and that will hopefully improve your, the speed of your algorithm. And there is something that is, to my opinion, still a statistical question is, okay, the choice of this lambda mean, like the smallest value that you want to visit, is an open question. It's something that is fixed in advance by the practitioner, but it's very hard to make it automatic in a way. So even though the packages will give you some answer with a fixed grid, you have to think about it. There is something hidden in this choice here, and it depends on the nature of the data set. So you have maybe to play with it a little bit. So I'm not going back too long in this. It's just we're going to use the same tool as yesterday. So you remember I introduced the gradients and the subgradients when it's non-differentiable. So we're going to reuse that quite extensively. Remember, it's just a tangent below my function. The slope of the tangent is just a subgradient. And the notation partial f is for the set of the different direction. So so the Fermat rule, you remember the minimum is where the slope is 0, and this is the same even if it's non-differentiable. It's just if 0 is a direction where you can put a tangent below, then it's good. So this is the same. We have seen also that for the L1, or the absolute value, it's very easy. We have only two regimes: the regime where it's smooth, and here where there is a 0. And so the subdifferential was just -1, 1, like -1 here, 1 here, and the set in between. So this is just a recap on what we have seen yesterday. Another point of view, I was given something even more general, but imagine that X is even simpler than we have seen yesterday. X is the identity, which is kind of stupid. Let's imagine that X is identity. So what you will be solving is, in fact, what I introduced in the end. It's the proximal operator. So in this case, my Lasso problem is just solving this optimization problem. And at the beginning, you don't know if it's unique or not. But in fact, this function is strictly convex. So if you add a convex function to a strictly convex function, the sum of the two is strictly convex. There is unicity, which is good. And then we can separate the different elements in the sum, again, as yesterday, because it's separable. So all I have to do to solve this problem is to solve it component-wise. And component-wise, we have seen yesterday that solving this problem will be the soft thresholding that we have seen yesterday. So this is just the computation we have been doing for a while. So this is our good old friend, and it's coming back. And maybe something that I didn't insist too much on this, but remember, the soft thresholding is 0 between minus lambda and lambda. And then there is a bias. There is this shrinkage factor here. So I contract the coefficient by a factor lambda towards 0, which means if my coefficient was large, it should be here. But in fact, what I produce is something a little bit smaller. And the reverse is true if it was negative. Just you put it toward the correct direction. Okay, so this is something we have seen. So now we need a new tool for what I'm going to present today. And this new tool is the duality, the duality in optimization. So it's something, when you start with a primal function, so primal means, okay, that's the original problem you want to solve. In our case, I call p lambda beta the function here, which is the one defining the lasso. So this is the original problem, so I call it the primal problem. I can associate to it a new problem. So for the moment, I'm just giving you what is the value of the problem. So this is a new problem. And we're going to analyze it a little bit. And I give you how this problem appears in the following. So let's look at what it is. So first, theta, it's going to be a new variable. It's living in another space. It's no longer in Rp, the set of the coefficient. It's living in Rn, the set of the signal. So we have changed quite a bit of word. And the problem I'm solving is more or less, if you analyze what's going on here, it's something that is quadratic with respect to theta. There is a minus, so you can put it minimizer. And I have a constraint here, so I need my theta to be what I call dual feasible. And what I mean by dual feasible, I need theta to be inside this set of constraints. And it is a polytop. It is a set where I need the inner product of theta with to be bounded by 1, so in absolute value. So they all should be inside something if you think about it, those are just like hyperplanes, and you get the hyperplane with a coefficient +1 and the other hyperplane with a coefficient -1. So it forms a polytope in the end. I will show you one of those later on. So okay, for the moment, this, which I will call the dual optimization problem, I can even reformulate it in a simple way, or more convenient, and we're going to play more with this, this formulation here. And it's just the following. So the theta, the dual optimal, first it is unique, which is a good news because I'm just minimizing a strictly convex function. And all I need to do is say, okay, I need to find theta that is close to y up to a scale lambda. So it should be, in fact, close to y over lambda. But I have a constraint. I need theta to be inside my polytope. So this, for those who have been playing with projection in Euclidean space or Hilbert space, is just a projection over a convex set, which is a polytope of the constraint. So let's try to motivate how we end up to this dual solution. This is a motivation here. I'm presenting just the notation with the general f, because I'm not going to give you the details for the generalization of the lasso. But if you substitute to the L1 norm and to the data fitting term f something more general, you can redo exactly the same computation. You will end up with the same kind of conclusion that I will give. So the motivation to give you, well, let's say the way to go for the dual, the simple one, is to say, okay, here's my optimization problem. What I will do, I will add a new variable, and this variable is going to be just y minus x beta. So what I add is just, okay, I add a constraint, and that z is equal to y minus x beta. That is adding a new variable in my model. But now the function here is way simpler. It's just quadratic without any constants or whatsoever. And you're aware, or I hope that you're aware of, when you get constraint optimization problem, you can compute the Lagrangian formulation of it. So the Lagrangian here is just, I take the function that I wanted to optimize, which is exactly this value here. And what I have to add is the constraint. In my case, is just I have to add z, or y minus x beta minus z is equal to 0. So what I've been written here. And the multiplier, the Lagrangian multiplier, is referred to as theta in my case. So it's n, which is, if you remember, exactly the dimension I'm interested in here. Because I got n constraints. I have, in fact, this is a vectorial constraint, so all the coefficients need to be the same. So I play with that and say, okay, when I do optimization, if I'm in a good case, and this is what I'm going to assume, it's a case where what happened, strong duality holds, minimizing this problem, or minimizing this problem, can be recast as minimizing this problem with, I take the maximum over the Lagrangian multiplier. So this is, okay, this is something you might find in the Boyd book, for instance, if you need a good reference for that. And so the cool part with the strong duality, it means just that I can flip-flop both of those terms here, the max and the min, and just compute what's going on and see if I can understand more my problem. So now I've been doing that, so the max is in front of it, and the minimum is over beta and z. But I can separate both of them, because my function is fairly easy if you look at it. So I will separate the terms that are from either the z or either the beta. So there is a part which is this quantity here, fz minus the inner product. And I pretty much get the same quantity, but this time with the L1 norm, omega beta, sorry, with some kind of term that is the same. If you look, those are inner products because of the transpose. And there is a term that is not very interesting because it doesn't depend on beta or on z at this stage, so I can just put it aside. And so all I get now is just, okay, if I define, in fact, it is something that is well known in the literature. It's called the conjugate function. I can say, okay, all I have to do is maximize this function, minus this function, plus the term that was remaining here. And if I do the computation, which is, but you can do it, you just end up having this one. So I'm giving you the ingredient needed you will have to compute what is this Fenchel conjugate function, which is, if you look at that, it's natural to use this function because it's just appearing here. This is what I've been appearing here. Up to a sign, there is mean of f minus something. The real definition is with a sub. It's just you use a minus sign. And there are some good news. I'm not going you to explain you those in details, but if you get f that is a square divided by 2, like the conjugate is exactly itself. So since I will be playing with f, computing f étoile is easy. It's just itself. And then I need to compute the conjugate function of a norm. There is a general result that explains to you that, in fact, all you need to understand is the dual norm to do that. And the dual norm of the norm, this is something that is quite easy, especially in the L1 case. The dual of L1 is L infinity. If you get an LP norm, it's the LQ norm with P and Q being conjugate. And it has just this simple formulation. So it's just the supremum of the inner product between X and Z over the unit ball defined by your norm. So, okay, you can just play with those properties, and what you end up having is this dual solution. Well, the dual problem, sorry. And we're going to rephrase it that way. So let's see what it gave us. So the original problem is I get my signal, I know it, I have lambda that I'm willing to use for my lasso, and there is 0 that is here, which is a very particular point. And now I want to design and show you something, which is what is a dual set, delta of x, which is a set of theta that are having this inner product bounded by 1. Well, in fact, it's a polytop, so I can just draw it as here's something like an octagon, or hexagon, more precisely. And the idea is my problem is to project on this set. So what I need to do to find the dual solution is to say, okay, I want to find the closest point in my set in orange that is the closest to y over lambda. So this is my new problem. If I can solve that, I will be very happy. You'll see, in fact, if you would know how to do that, you can solve the lasso very efficiently. So it's as difficult as before. It's another point of view on the same problem. And we're going to see we can use that. So let's analyze it even more, because for the moment there were 2 problems separated, but in fact there is a very intense relationship between the 2. So if I take beta as a primal solution, one of them, and I take the unique solution of the dual problem, in fact there is a close connection between them, which is the following. It's like y, the signal, is equal to x beta, the optimal solution of the primal, plus lambda times the dual. So if you can just rephrase that in terms of residual, it could be y minus this element is the residual, is more or less a rescaling of the dual variable. So the dual variable is a scaled residual. This is pretty interesting. And we have seen yesterday what were the Fermat rule in our case. And in fact, we have been using the residual in the Fermat rule. But now I can simplify it just by using, and I can go and rephrase those Fermat rule, which tells you the following. For any variable, the inner product between my atoms and solution, they should be very restricted because they can only be plus or minus 1, depending on the sign of the primal solution, or when it's different from 0, or when it's 0 for the primal, then this inner product can be in between minus 1 and 1, which means, more or less, you have to be inside this polytop. This is the interpretation of it. And we have seen yesterday that there is a cool consequences of that. That was the creation of what I call the mother of safe rules. It tells you what is the critical lambda. And what is the critical lambda? We have seen that if I take this value, which corresponds to computing exactly these elements, then 0 is the solution as soon as lambda is greater than lambda max. So all you have to do to check that is just say, okay, if beta is 0, all the coordinates are 0, and if I can say xj transpose a residual is inside of this, then I can guarantee that I have a solution. And in fact, that's possible as soon as I take y over lambda as this quantity, y over lambda, because if I take 0 here, y is equal to lambda times the dual solution. So I can just do that and convince myself that the lambda, the critical value of lambda, I can get it. And the only thing that I'm going to prove it to you is just that yesterday we were using this, and now I can remake a link between the two elements, between the primal and the dual. Yesterday we have proved this in a way. It was just the Fermat condition. But it was proved for this value, y minus x times this quantity. We had no interpretation of this dual point. So let's see where it's coming. Well, it's just from the fact that you're playing with the Lagrangian, and you start to compute the first order condition. You want the Lagrangian to have a partial derivative that is 0 with respect to z, with respect to theta, and with respect to the last variable, even though it's not differentiable. And so if you compute all of them, so the Lagrangian with respect to z, this is just, there is this part here and this part here, so it's something that is quadratic, linear, so I can compute it, and I just get this constraint here. So z is equal to lambda times dual solution. With respect to theta, then all I've got is this constraint is satisfied, which is the usual. You created for the Lagrangian a constraint optimization problem. You want the constraint to be satisfied. So all I have to get is just this quantity is equal to 0. And the last one, this is the one where you get a non-differentiable term because of the lambda, of the lambda, but of the L1 norm. And we have seen that the condition just tell you that we have something where 0, should belong to the partial, the subdifferential, of this quantity. And if you reorder those different terms, what you interpret, and this quantity should belong to the partial of omega. And in fact, this is exactly equivalent to say, okay, for all the atoms, the inner product should belong to the partial differential of the L1 norm. And this is exactly this quantity that we have computed yesterday. So we are back to what we have learned. So let's see something that is interesting now is let's interpret what is the critical lambda max. So if you look at this picture, I showed you before y over lambda, its projection over it. What's going on all over this line is just the elements are proportional to y. And there is one moment, in fact, it's when you take lambda is equal to lambda max, where the point is exactly in the set. So if you take lambda greater than lambda max, you're already, and if you project in the set and you are already in it, you don't have nothing to do. So this is why the solutions are easy to compute when you get lambda that is greater. And like this is exactly the critical value. Then, well, now you need to start thinking about how you're going to optimize something. And we're going to extend those elements to understand what I mean by the Ceph rules. So the first stuff is, let's go back to the Fermat rule and interpret what it tells us. And what it tells us is something very interesting, is like, if the inner product are strictly smaller than 1 in absolute value, then I know that the solution of the primal is 0. So that would be very lucky that somebody will give me that, but if I know that, I can assure that it's 0. It's just, this is what was written here. If I take something and the inner product is in strictly between -1 and 1, this case cannot occur. So it means that the only case that can occur is beta j is 0, and the inner product is inside of this. So that would be great. That would be, okay, wow, that's cool. Solution is 0. I don't compute the... Of course, that will not happen. Then this is just something that you can hope for. Because this is your target, almost. This is residual at the optimal value up to scaling. So there's no way you're going to know that. You're never going to know that. In fact, you're going to know it approximately someday, but that's all you can hope for. But on the other hand, maybe I can construct what I call a Ceph region, which is inside Rm, and that contains this dual solution, So I know theta hat will belong to this region. And if I can say, okay, now it's not exactly this value that I know that is strictly smaller than 1, but it are smaller than 1, I can remove GS coordinate of the primal and put it to 0. So this is the good news. Now my objective is to say, okay, I will have to design safe regions in a very interesting way so that they are as narrow as possible, because I would like them to be very precise, so to be very close to the single point that is the solution. And so let's try to make it small. And also I need to make this computation efficient, because you will have to do it in algorithm. So if the set is weird and very complicated, you might not be able to compute this quantity. So you have to be aware of the price to pay by considering these calculations. So that, let's say, fairly is to say, okay, why not trying to take a ball with some radius C and radius R and center, and let's try to compute exactly this quantity and see where it's how it does. So the problem is just like, let's try to say the supremum over this ball of the inner product between a vector and theta inside this ball. Well, in fact, you can just use Cauchy-Schwarz, and the answer is the following. You take the inner product with the center, which is easy. It's just one inner product. And you add the price, which is R is a radius, and the norm of X that you have to shift a little bit. So in fact, now, for those kind of safe regions, what you will have to test is just the following. I compute the inner product in absolute value. I add a little bit of correction with respect to the precision of my safe region. And if it's smaller than 1, and then I'm lucky, I can remove the GS coordinate of the equation and forget about the GS variable. Xj is no longer in the problem. So now the objective is easy. It's like, I want to find R as small as possible, because that will be a very precise region. And of course, I want to find C as close as possible as the unknown dual solution. So I want to make a ball that should be closer and closer to the dual. So let's see what you can do. There is one that is very easy, proposed by a team by El-Gawi and co-authors. It's very geometric. You said, okay, I know that this point is dual feasible, because y over lambda max is inside my polytop. What I can say? I can just say, well, you know, if this point is in the polytop, and this point is a projection, this point is obviously closer to y over lambda than y over lambda max is close to y over lambda. So all I can say is just like, okay, I can draw a ball centered in y over lambda that going through y over lambda max, and I know this point will be inside of it. So it's easy. I can, this is easy to compute. The radius is easy also to compute. It's just, okay, y over lambda max minus y over lambda. You take the absolute value. So you can compute the radius. And the center is very easy. It's just your signal that you have recentered. So you divide by lambda y. There's nothing almost to do. And so with that, well, now I can exactly apply this. And in some cases, I will be lucky that I will remove some elements in my computation. So even something you can do before anything in your algorithm. So you don't have even to like start the algorithm. You can just say, okay, let's compute y over lambda, this quantity, which is more or less the norm of y divided by a quantity that you know. So you just know you need to compute lambda max, which you have to do anyway. I told you, you need to start by computing lambda max to know where to choose the lambda in the first place. So you can do that. But there is a limitation if you do that. And the limitation is the following. So this is like the description of the ball I've given to you before. Well, you can check that, okay, this is a rule with the radius that I considered here and the center I consider here. This is just a rephrasing. But the limitation is if you take too small, your rule is going to be useless. As soon as lambda over lambda max is smaller than a quantity that is not important in itself, but just as soon as this quantity, well, sorry, as soon as lambda over lambda max is smaller than this quantity, you cannot screen anymore. And we're going to show that in the simulation. You will show that there is a barrier if you're using this very simple rule. It just, okay, it will work at the beginning for large lambda, and the more lambda goes to 0, well, there is a moment where it stops being useful. So you might be doing computation for nothing. And so there is also another point of view that I today. We were talking about screening rules, the old screening rules. And if you interpret it exactly this quantity, look at what it's going. It's just I'm computing the inner product between the atoms with respect to the signal. I check if it's smaller than a threshold, and if it's smaller than a threshold, I remove them. So the cool part with the screening rules is, in fact, they tell you, like, for the lasso, they are well-funded. They are just telling you, if the threshold is selected with this value, well, screening is exactly well-funded in a way that at the end, you have screened only variables that will be inefficient for the solution. So it is some regard on like an old strategy, but I think it's very interesting to understand this part. But we will have to go a little bit further. This is something that was introduced, and that was the motivation at the beginning of my work with my colleagues. That was from a paper from Bonfoy et al. They are a team in France. And they were saying, okay, we were using in the first place y over lambda max as a dual point. But the strategy could be the same for any dual point. If somebody gives you a dual point, I know that, okay, I can compute the distance between the dual and this point here. And I know that my optimal solution will be inside this ball. Because if it's a point is here, I know this one is the closest to this point, so reasoning works again. So all I have to do is to try to compute a value of theta that is, and is maybe more interesting than the one I had, the y over lambda max. And the good news is those authors, they say, okay, well, let's be clever in a way. So we know that if we add the optimal values, there is a connection between the primal and the dual. And it's just, I can compute a dual point by just rescaling the residual. So proposed was fairly easy to say, okay, well, at any time in my algorithm, I can compute the residual. And we have seen yesterday that we needed the residual, for instance, for the coordinate descent. So I compute the residual. I rescale them so that they will be inside the polytop. And that will be a reasonable choice for a point that is dual feasible. So all you do is just, I take the residual and rescale them. So the rescaling itself is not necessarily very important, but it's just telling you that I take the residual, rescale it, and then I got a point that is inside my polytop. And okay, those quantities you can compute them quite efficiently. It's not too much to do. So what you do is the following: you take your residual. They are somewhere on Earth. You don't know where. But what you do is now you just take the point that is proportional here to this rho k, which is the first one entering the polytop. And this is exactly what the operation is doing. And now note that it is very easy because it's not a projection in the same way. It's just a rescaling on the line. So you don't have to project on a difficult set. It's just rescaling. That's something that can be done. So it's limitation on that. The limitation is, even if you give me the best point, which is the one that you want to obtain, the best ball that you can create is this one. You cannot be better as long as you center the safe region on this point here. So the starting point of the work we were doing with my colleague was like, it seems to be not natural to start with this point. Maybe we should start somewhere else. And the idea was like, maybe starting with a point outside of the polytop is not a good reason. Let's try to focus more on the dual point, and let's try to center it somewhere else. But before that, there is another aspect of the strategy. For the moment, the safe rules I mentioned, they were given to you in advance. It's more, I haven't done any work, I compute the safe rules, I disregard some coefficient. And then I would run an algorithm. There is something more interesting. Also, I told you now we are interested in computing maybe 100 lasso. So 100 lambdas are involved. So what I get is I start with lambda 0. For instance, it's lambda max. And then I got smaller and smaller values of lambdas. But the point is, when I start, for instance, focusing on one element, let's say the TS1, I have computed all the previous one. And the one that is just before him or it is just very close. So what I can do, and it's something that most solvers are encouraging, is to do a warm start. I told you when you do optimization, usually you have to start somewhere. And the better the starting point, the better your algorithm. In those cases, the best you can do is to say, okay, I'm going to do a warm start. I'm going to take the solution I obtained at the previous step and feed it as the initialization for my new step. So I want to compute for lambda t minus 1. Sorry, I want to compute for lambda t, and I take the initial value as a previous solution. And this is for the primal. And some people around Wang and his team, they were saying, okay, why not using also the information from the dual point of view? Because everybody is using this information anyway for the. But maybe we can use the information from the previous step to get a better dual point. And so I can use this dual point to create these kind of regions, and they would be better. So this is more or less they only got an issue is that in their work, they assume that they would know exactly the solution, the dual solution. And again, it's impossible. Well, it's possible in only one case, which is when you're starting at lambda max. It's a solution of an optimization problem. So you will never get this guy. You will know it up to some precision, and we're going to discuss what precision we can hope for, but you can never know it exactly. So to assume this. And this is also one of the motivation of our work, to just told to this team that, okay, you should not do that. You cannot be sure that this guy is the one you expect. And in fact, if you were trying to like check their rules and see if they can compute the real solution, well, you can check it doesn't work. So what I've been plotting here is something with respect to lambda. So it's a log scale. So the greater lambda are on the left, the small lambda are here. And here, this is, we're going to see it later, the log duality gap, which means it assesses how precise is my solution. So if I am minus 10, I'm very precise, and if I'm over there, the precision of my algorithm is not very, very efficient. And different strategies, the one that I'm going to produce to you later on, and the one from the other team. And what happened is, here you define a threshold, which is the precision of your algorithm. So we would like to solve the lasso at this precision here. And what happened is, if you're using rules below the threshold, so if you want, here it's like 10 minus 1 or something precision, then okay, you get it. But if you're using the strategy from the previous team here, the problem is like sometimes you will produce solutions that are not even satisfying the criterion you choose in the first place. So you think that you find a good solution, but in fact, they are way above the threshold that you want. So you should be careful with that. And let's see what is the duality gap now in this slide. So we have defined the primal. Again, this was like this quantity here. I call it P lambda. I defined to use a dual objective, and it was this quantity here, and remind that I can only access those elements when theta is dual feasible, so when it's in the polytope I mentioned. And now what people call the duality gap is the difference between the primal and the dual. So it's just, I will call it G for gap, and it's just primal minus dual. So I need to apply the primal to a point beta of the correct size, and the dual for a point that is feasible. And the good news is that if I compute this quantity, which you can, that's something, I mean, you just have, okay, to do a bunch of operation, but you can do it. Then we're going to see that there are some interesting consequences out of this quantity. And where is this coming from? It is from the strong duality I mentioned to you earlier. So the strong duality is what it's telling you the equality here. And if we go back to long time ago, to this here, the strong duality was telling me I could flip-flop the mean and the max. They were telling me the dual value and the primal value are exactly the same. And this is what I'm at so. Yeah. So this is strong duality assessing this property. Just I can flip-flop the min and the max. So let's analyze what it tells me. The primal value at one point, well, it's 1 point, but I know that beta hat is the optimizer, so it should be the minimizer of this quantity. So for any point beta, the optimal solution is smaller than the other one. Now the same is true for the dual. The dual, remember, I was maximizing over the set of constraints. So the dual point taken at any point that is feasible is smaller than the dual solution. So now you get some kind of, because this is exactly the value you want to obtain in your optimization problem. So if you knew it in advance, okay, you're done. You're lucky, but you don't. But now I know I can compute for any beta this quantity, and for any theta this quantity, as soon as theta is dual feasible. And the good news is that the solution is in between those two values. So if I compute the difference, which is exactly the duality gap, first it's positive, so it's a good news. You know where it is. But then, if the duality gap is smaller than epsilon, well, you get a sandwich. And so if you know that in between this guy and this guy, there is epsilon, well, you know where is the solution. It is just in between those two guys. So what you have, if the duality gap is smaller than epsilon, the primal taken at your beta, your guess, was it a good guess or not, you don't know. You know now that if the duality gap is smaller than epsilon, then the difference in terms of function objective, and that's a very interesting criterion to stop algorithm. It's way better than saying that, oh, the two iterates are almost the same and I should stop my algorithm. Or I compute the objective value and I detect that the objective value is no longer changing and I stop. And you know that you get many weird behavior with like sequences. And so it's not because like two elements of a sequence are very close that it has converged. It could be like very slowly converging. But here, this is another story. It just tells you that if you can compute the duality gap, and you can, worst case scenario it's slow, but you can do it, then you get a criterion assessing the precision of your strategy. And this is something that is used in most solvers. Like, as long as you can compute this quantity, you should rely on it, because it's way more precise than anything else. We can use that now. Well, I'm still using this duality gap. So this is the same notation as before. And what we is to say, okay, I told you we're going to switch our point of view. We're going to take a safe region that is centered on a dual point, on any theta. And then I will compute a that is up to some simple transformation. I'm more or less not giving you the detail, but it's just some simple algebra tells you, like, if you compute this, you can guarantee that this is a safe region. It means that you know that the real solution, the dual solution, is inside of this element. And it's more or less just playing with, it's more or less just playing with this property here. You just take the correct scaling and you will obtain this, this element. And there is another good news is primal algorithm is converging. Well, okay, you have used algorithm and you know it's going to converge. So this is what you should do in practice. Well, in fact, you also check that the dual is converging to the dual solution. Then, of course, I told you before, the duality gap should go to 0 because, well, it's a sandwich. So if both guys converges to the solution, then the difference between the two should go to 0. So in a way, it means that it's behaving okay. Like, you know that the element that you're computing here are going to 0 at the correct speed. So I'm just going to skip this. If you're really interested in the computation, you can do that. But so let's go back to what Bonnefoy and Koser were proposing. It was, I center the ball here, I take a large radius, and the best I could get is like this small, well, at least this radius here. But now, if I take a point that is inside my polytope, and I produce points that are going closer and closer to my dual solution here, well, then I can compute something with a radius that is going to 0. So the ball is going to converge, and it's getting more and more precise. I'll be able to remove more and more variables all along the way. So for that, I will present you just how it does these elements for the coordinate descent we have seen yesterday. So I'm going to present it in detail. All I need now is to say, okay, to create my region, I need dual points and the radius. So the radius, I told you, it's the duality up to some kind of scaling. So I can compute it. All I need to do is take a beta k, which is the case iteration of my algorithm, theta k, which was constricted as we did before, a rescaling of the residual. And now I can compute I have this ball, so I can compute the rules. The rule was just, can I compute exactly those elements? And so it's just taking the product with respect to like theta k, the current residual or dual point that you get, and then add this little price for the duality gap and the normalization of the x. So this one is, I know, long, but let's go and analyze what we're going to do. We really are interested in solving the lasso for, let's say, 100 value. T is large. So the input is the X matrix, the design, the signal Y. Epsilon is the precision at the level at which you will say, okay, I'm satisfied with this solution. So think about it as 10 minus 6, 10 minus 8, 10 minus 10. There are a few coefficients more. So K is how often should you compute the screening or computing the duality gap. There's a price to pay for computing the duality gap. So maybe you should not compute it too often because that will slow down the process. So just don't do it every step. So there is a quantity for that. K is the maximum number of iteration. So F was how often you compute the duality gap. And those elements are the lambda t that you want to compute. So you want to compute t of those values, maybe t minus 1 because 1 is already given. So what you do is a loop over all the lambda t's. Okay, you start with the largest one, because you know if you start with a large one, it's 0, and you will produce like the following one. You do a warm start, so you put the previous solution in your first case, and then for your budget of how many iteration you are willing to do it, so it might just be a constraint on your system. If you can afford 1 million iteration, maybe you should do it for it, but most likely you can only afford for like 1,000 or something more reasonable. So from time to time, so every F period, you're gonna compute the duality gap. So it means that you compute a dual point. You check. If this dual point gives you like a criterion that is satisfying, you stop the algorithm. It's over. You're satisfied. You got an epsilon solution. Otherwise, well, you keep on, like you update your element, and you are interested now in going for the next one. So at this stage, it's just stop or computing the duality gap. Those are the only operations. The real part of the algorithm is the coordinate descent we have seen yesterday, and doing soft thresholding. So ST here is what I denoted yesterday. Sorry, eta ST. So it's the soft thresholding of the residual at the scaling corresponding to the current one. And so you have to do that. So this is the original algorithm. This is the kind of software that is coded in most packages. And now let's see what the difference when I add the screening rules. So all I have to add is the following. I have to add a set where I compute the active set. This is why I call it A. And there are all the elements that satisfy the test, which say, okay, this variable is active. I have to keep it. So those are the active elements. And I can remove like the ones that are below the threshold I mentioned before. And then what I can do is I don't have to loop. Before I had to loop over all the coordinates because I didn't know which one were interesting. Now all I have to do is say, okay, now I know the active ones. So I just have to loop over them. So if the active set is very small, you have eliminated a lot of variables, then this is going to be very efficient. You're going to just go over a small set, a small active set. And that's performed pretty well. So let's see in practice what happens. So here in this plot, I will show you in this direction, you get the lambdas, or more or less a lambda rescale. So here, it's when you get lambda max, and over there, it's like small lambdas. So the scale is reversed, sorry, with respect to yesterday. And we get different methods, and those methods, all of them present something. The scaling on the left axis is just the number of iterations. So it's how many iterations you have been performing. And those are different methods. So this is an algorithm where you just don't do any screening, and those are different strategies. Now the color plots tell you, like, if it's blue, it means that I'm using all the variables. I have to use all of them. So if I don't do any screening, well, I have to test all of them and do the coordinate descent over all of them. Then I present like the result from El-Gawi and Bonnefoy, and they propose some safe screening rules. So in fact, you can check that there is a critical value where before this critical value, it's interesting, you can remove a bit of variables. It's red, so it means on the left part here, a lot of the variables are eliminated. There's only like a few, the proportion is close to 0 of the active variable. Now the good news is with the work that we proposed, we are like able to like discard a lot more variables. So it means that here they were limited by just a threshold. Like for instance, it was this value here, and you cannot go further. Now with our methods, you see that the more computation you allow, so the first line means you get only a few iterations, and if you go down on the line, it means you have been iterating a lot. Well, you see that you remove more and more variables. So it means that you can go further because you can eliminate, maybe like here you eliminate almost like 90% of the variables. Okay, if you are in this region, it starts to like it's not as good as before. But at least you have win maybe a lot of time during all this period here. And this is something you can see. So let's check the following. Same data set, so maybe I didn't present the data set. Common data set in genomics. It's set. So it's really with the size of what a genetician, statistician have. It's like a few number of patients. Here it's like 72. And many genes that you try to like exploit. And there were, for instance, like 7,000 genes that they are trying to use. So there's a lot of variables, and there is a lot that you want to remove. And let's now in terms of, this was just the proportion of activated variables. Now this is like practical improvement. Here, the duality gap, so how precise you are. So if you are not very precise, the time, well, obviously it's very fast. Okay, you want the solution with low precision, so it's very efficient. But now if you improve the duality gap, it means like you need to add more and more computation because you want to be more and more precise. It means your precision is 10 to the minus 2, 10 to the minus 4, 10 to the minus 8. And those are the different strategies. So the no screening is the usual, so it's in red here. So you see at the beginning it's not too bad. But as long as you start demanding more precision, and for instance, when you are very precise, it takes a lot of time in the end. If you compare with the different strategies, the one from El-Gawi and Bonnefoy, you see that in fact, they are not really helpful. They are a bit helpful. There's a price to pay for doing the screening. The screening is not for free. You have to do a testing. And if the testing is not helping, well, you pay the price for doing it. So sometimes it's even worse or on par, or at least it's not very helpful. The good news is like with the gap-safe strategy that I presented, well, this you get. Those are two variations of the same idea. I presented you only the sphere one, which is the yellow one. But you see that there might be a huge improvement if you demand high precision in your solution. So this is particularly important. So let me wrap up what I've been doing here. So it's presenting new safe screening tests for improving this in this kind of algorithm. There are some kind of convergence guarantees, so you know that in the end we're going to identify the support. This I didn't really mention, but you have to know that in the end you are sure of the support that you found. We have applied this for coordinate descent. I told you it could be done for other kind of algorithm. It's just up to some point you have to choose your favorite one. Of course, I mentioned that you can use that for more general regularization. It could be done for ElasticNet, which is almost for free. Group Lasso is a little bit more involved. All you have to do is change the norm. It used to be L1. You apply that to the one that you are targeting, or the one that we have seen yesterday. You can also change the data fitting term. So for instance, we can handle also logistic regression, which is important for people application. There is only a little restriction on the smoothness of the function you can do. Okay, you cannot do that with any kind of function. There is some limitation. And we are actually working on the sparse group which is a bit more involved for many reasons, but hopefully it should be done for February, I would say. Let's be optimistic. And so if you need more, the two recent papers, one at ICML in and the part on the multitask is appearing in NIPS next month. And so the Python code is available on demand. We are put on scikit-learn, so it will be online soon enough in useful packages, so you might try it as well. And I should thank you now.